Hello all, Dr. Caudell here, and this video recording is going to be some highlighted topics, and I'm going to show you my work and these different practice problems. So follow along with me, and I'm going to again talk through some highlighted topics from Chapter 1 and show you how to work specific problems in Chapter 1. The first topic we're going to talk through together is distinguishing mixtures from pure substances through their physical properties specifically. So in ALEKS, when you're presented with problems like this, you'll see example problems like sample A is a solid yellow cube with a total mass. The cube is ground to a fine orange powder, so we know something about the color, and added to 500 milliliters beaker full of water. The beaker is stirred vigorously. Some of the orange powder settles to the bottom of the beaker, and some rises to the top and floats on the water. So with problems like this, I like to draw out what's being described, find something that works for you. So if we have beaker of water, and let's say it's kind of a blue color, and then we are told that we dissolve a solid yellow cube, and then some floats on the surface of the water and some sinks to the bottom. Then the next part of the question, we're told that the powder at both the top and the bottom of the beaker is filtered out. So this is filtered out separately than this portion, so the top and the bottom portion. So right now, sample A, what you should start to think about as far as physical properties is going to be the property of density. You'll see density represented like rho, like this. This is the symbol rho. You'll also see it as a lowercase d. So what we can tell right now with water is it has a certain density of 1 gram per milliliter. Also, you'll start to get used to the units of density being mass over volume, where mass can be grams or kilograms, volume, usually milliliters, can also be represented as liters. Another way to remember the meaning of density is that density equals love, because this together, M over V, kind of looks like a heart. So now going back to sample A, we know that water has a certain density, but then this has a different density, this part of the substance, and this has a different density than water. Specifically, what we'll get into is that this top portion, if it floats on top of water, that means this part is less dense. Then what we'll get to as well is if that something sinks or goes to the bottom, that means that this is more dense. So that was the setup of sample A, and let's go back and also look at sample B now, and then we'll talk through both of these as far as if they're a mixture or a pure substance. So for sample B, we're told that we have a certain amount of mass of a coarse gray powder with a faint, unpleasant smell. 15 milligrams of the powder are put into a very thin tube and heated, so maybe a thin test tube. And we're told that the powder is heated, so probably under a Bunsen burner, which we will look at in lab together, and we'll use Bunsen burners. As we're taking at melting temperature, this could also be a melting tube, capillary tube that's very thin, and you put a powder in it, then you heat it, and then you keep track of the temperature, and it will go in this little device, and it'll tell you the current temperature, and you'll look and see when the solid starts to melt into a liquid, and you'll record that temperature. So that's called a melting point apparatus, and we do have those in lab at FRC. So now sample B, the powder begins to melt at 66.2 degrees Celsius. So it goes from a solid state to a liquid state when it melts. Importantly here, we're told that all of the powder melts at 66.2 degrees Celsius. And then once that all melts into a liquid state, then the temperature starts to rise again, eventually reaching 76.0 degrees Celsius. So before we get into the answers from this first practice problem related to mixtures and pure substances, let's review a couple things about mixtures. So one thing is that neither sample A nor sample B will look like a mixture. An obvious mixture would, of course, be something like salad dressing, where you can see all the seasoning and separation of oils. Also, an obvious mixture would be trail mix. You can see all of the individual components in trail mix, like M&Ms, seeds, nuts, things like that. So with our samples A and B in this problem, both are the same color and texture, so that makes it a little bit more difficult to tell just based on a visual appearance. Is this a mixture? Is this a pure substance? In chemistry, we'll talk a lot about macroscopic versus microscopic views, and something that is seen or not seen by the naked eye is called something on the macroscopic level. So from the macroscopic level, from just visual appearance, we can't tell if A and B are indeed pure substances or mixtures. So to solve this problem, we do need to think about those physical properties like melting point and density. And now more specifics on mixtures. So we might be able to look at a heterogeneous mixture and say, just visually, if it appears to be a mixture, because we could see the individual components. As a heterogeneous mixture is defined as the composition is not uniform throughout. On the other hand, if we have homogeneous mixtures, then these look the same throughout, so that it's harder to tell if it is a pure substance or a mixture, especially because these homogeneous mixtures do visually look the same. So again, for cases like these, we need to go to the microscopic level and look at some physical properties to be able to tell. And then this wasn't explicitly stated yet, but a mixture is defined as a combination of two or more substances in which the substances, this is an important part, retain their distinct properties. One example that comes up in chapter 1 of a mixture is if we have a glass of water and we actually have sugar that's dissolved in it. So sugar is usually a molecule that looks like this. These are all carbon atoms and hydrogen atoms. Don't worry about this too much right now. We will get into bonding towards the end of the semester. But the important part here for mixtures is that the water molecules themselves will definitely retain their distinct identity and distinct properties. And then the sugar molecules as well will also retain their distinct identity, even though they're mixed into a mixture of water molecules. You will still be able to distinguish sugar molecules within the water molecules, only at a microscopic level though. So again, the simple mixtures you can usually tell on a macroscopic level. So salad dressing, that definitely appears to be a mixture. But with some of the more complex mixtures or more subtle mixtures, it might be hard to tell just visually, especially for cases like this, for example, water and sugar together. You wouldn't be able to look at a glass of sugar water and say, hey, that is definitely a mixture. But on the microscopic level, it is indeed a mixture where the sugar molecules and the water molecules do retain their distinct identity. Now, I mentioned that some mixtures are easier to tell if they are a mixture, some are not as easy to tell. So if we're going to look at the microscopic level, there are some factors we can keep in mind when trying to answer questions like this. The very important factor to keep in mind here is that we can use physical properties, use the fact that physical properties of pure substances are precise and constant, while they're often variable for mixtures. An example here that relates to our sample B is for melting point. So say we had a mixture of solid where some of it was this purple solid, another part of the mixture was this red, but let's say that we couldn't tell just visually that there are purple and red components or purple and red molecules. So if we were to take the melting point of this mixture, then the purple component of the mixture will have a different melting point than the red component of the mixture. And so as you start to melt a mixture like this, again, you might see the purple component melt maybe earlier, and then you go up 10 degrees Celsius, and then finally this component of the mixture goes from a solid to a liquid or it melts. So if you do have a mixture, then the two components in that mixture will likely melt at a different melting point, unless they're very, very similar as far as their properties, but that's usually one way you can tell if you have a pure substance or a mixture. Again, a mixture will have components that melt at different temperatures, while a pure substance will all melt at the same temperature. And now we also did work with sample A, so other examples of physical properties other than just looking at the different melting points. You can use any of these physical properties to be able to say if you have a mixture or a pure substance. And for sample A, we specifically were looking at the density. Again, a pure substance will all have the same density, but if you have a mixture of components, then you might have one component with a certain density, as we saw in sample A, and then the other component of that mixture might have a different density. So that's how we could tell for sample A that we do actually have a mixture. Now, this problem was focused on looking at physical properties, but I also wanted to go ahead and point out that we do have chemical properties as well. For chemical properties, we think of those as being able to observe some sort of reaction that's taking place where the actual chemical properties like flammability, acidity or basicity, and reactivity, where these different properties are specific to, again, pure substances, and then they would be different if we had a mixture. As we move through the semester, this difference between chemical properties and physical properties should become more clear as we especially get into some concepts like acids and bases and reactivity and chemical bonding in this semester. Another important property of mixtures is that they're separated into their pure compounds through physical means. Why can we do that for mixtures? Importantly, it's because, again, mixtures are composed of two or more components, but they're very importantly, they're not chemically bonded to one another. So again, going back to that sugar and water example, the sugar molecules are not physically bound to the water molecules. They are more of a mixture where the sugar molecules are floating around and the water molecules are floating around as well. So because those two components of a mixture are not chemically bonded, then we could use a melting point apparatus to see if we had solid ice and solid sugar, for example, we would see that those physical properties are different for the different components in a mixture. And importantly, coming back to this definition, we consider sugar water an example of a mixture because those two components are not chemically bonded and they can be separated by physical means. Examples of physical means, go back and think about the properties here from this slide. So by physical means, for example, we could try to melt a mixture, we could try to boil a mixture, we could measure the densities of mixtures. So these are examples of using physical properties to help us pinpoint which physical means would be appropriate for trying to separate that mixture. Another big concept in chapter 1 is the idea of compounds. So compounds are examples of pure substances. The definition of a compound, they are composed of two or more elements. For example, H and O, so hydrogen and oxygen are two elements, and water is a compound because it is indeed composed of two or more elements. Now we'll get into drawing these structures further on, pretty later down in the road for this semester, but one very distinct property of compounds is that they cannot be separated just by physical means. Instead, to attempt to separate compounds into their individual elements like H and O, we would need to use chemical means in order to separate those elements. So generally, it's much easier to separate mixtures than it is to separate actual compounds like H2O into just hydrogen atoms and into just oxygen atoms. The key point from this slide is that mixtures can be separated by physical means, whereas compounds, which are examples of substances, need to be separated through chemical means. So now the answer here, going back to sample A, like we talked about, We knew that one component of sample A did float on water while another appeared to sink. So this component would have a density that is less than that of water. This component of sample A would have a density that is denser, greater than that of water. So because of this, because of what we knew about sample A, then we can say in the end that it is a mixture. Why is that again? So this component is going to be a different substance altogether than this substance. And remember, mixtures are combinations of two or more substances. Now our answer for sample B, we were told that gray powder all melted at the same exact melting point. So that means that at that specific temperature, all of that compound went from a solid to a liquid. So we weren't told that some of it melted at a certain temperature and then the other part of that melted at a different temperature. So because it all melted at one temperature, we can say for sample B, this is indeed just one pure substance. Now the next highlighted topic here is again related to distinguishing compounds and mixtures. So we've talked a lot about mixtures, elements. Those are all ones on the periodic table, like we know about oxygen and hydrogen. Those are examples of elements, for example. And O and H are the chemical symbols for oxygen and hydrogen, respectively. Now we've also touched on what a compound is. So it's composed of two or more elements. So now that we've defined these, and you can look back in your notes for a more detailed explanation, let's go through this practice problem that you might be presented with in ALEX. So we have substance X, Y, Z, and T, and we need to decide, are these elements, compounds, or mixtures? So before solving for that, let's cover just one more idea here that is introduced to you in chapter 1, and you'll see molecules actually more in chapter 2. So as mentioned, a compound is a substance composed of atoms of two or more elements. So like water was definitely an example of a compound. It has H and O in it, so that's definitely a compound. And again, you will see molecules more in depth in chapter 2. So a molecule is an aggregate of two or more atoms, okay? So similar to a compound. However, a molecule does not have to be composed of two or more elements. So now this next part of a definition of a molecule, so we can have diatomic molecules where they're composed of two atoms. So di meaning two, and then atomic for atom. Now I will point out here that in this problem, we're only asked between element, compound, and mixture and not a molecule. What I'm going into is to help give you a heads up for what you will see in chapter 2. So this next part of what can be a molecule is these different elements. So yes, just elements that actually exist as diatomics. So they exist as diatomics in their natural state. So for example, if we have oxygen, you will rarely see oxygen as just a single oxygen atom out in the atmosphere, for example. Instead, you will see oxygen atoms in the form of O2. And I'm giving you a preview of this as well. So these are lone pairs of electrons. You'll learn how to draw these again pretty later on in the semester. So what can get tricky here is knowing that these elements, the ones listed here, do exist as diatomics in their natural state. If they are not listed here, then they can exist as just their single element in nature. So for example, carbon or silicon, for example, you will not see carbon having to exist as C2 or silicon as C2. These specific elements, though, do exist as Br2, I2, N2, Cl2, H2, O2, and F2. Now, luckily, there is a way to more easily remember which elements do exist as diatomics, and we remember this by saying Brinkelhoffs. And again, you will see this more in chapter 2, but there's a little image that says keep calm and Brinkelhoff, meaning Brin, Cl, HO, and F. If you remember Brinkelhoff, you will then remember which elements exist in their natural state as diatomic forms. And now coming back to our problem here, we did cover what a mixture is, so let's move on and start solving this. So when we look at substance X, we should recognize what we just talked about, that this is definitely the same atom in red, but it is existing as a diatomic. Now, what can we rule out right now? Well, we only see that this whole substance X is just these two red spheres joined together. There's nothing else present in that box. So we know off the bat that that is not a mixture. Next, going back to our definition of a compound, that has to be composed of two or more elements. And right here, red and red, that's supposed to be representation that this is the same element just bound to another one of the atoms of that element. So from that, we can also cancel out compound. That leaves us just an element. More specifically, though, based on what you just learned, that element here is definitely going to be one of the Brinkelhoff elements. And remember, these Brinkelhoff elements in their natural state will exist as these diatomics. So this could be chlorine, this could be oxygen. It's definitely one of the Brinkelhoffs, and more specifically, it is still just an element. Next, moving on to substance Y, we see here a blue and red sphere. That's definitely one kind of compound, right? And then what we also see here, though, is this where we have two blue spheres and a red sphere. That's definitely different than this. So right off the bat, we can just say that this is definitely a mixture of two or more compounds. Next, moving on to substance Z, it's different than X because we see two blue spheres and a red, meaning that this is definitely not a diatomic, and there's definitely more than one type of element present, the red element and then the blue element. So, and that is the only thing that's present here is this blue sphere, then red. There's nothing else present, so there's definitely not a mixture. And then it's definitely not a diatomic element, so here we know that's a compound. The next one here for substance T, we can look and see, is there anything else present other than these types of molecules or compounds that have red, blue, and then red? No, that's all that there is, so that's definitely not a mixture. And then is this an element? Well, again, no, because there's red spheres and blue spheres present, meaning this is not a diatomic element. It's definitely a compound. Probably this is H2O, which is water. And we will talk more about how atoms bond to one another, again, later on in the semester. The next highlighted topic we're going to go through is distinguishing a chemical and physical change. So we did talk about these earlier on in this recording, and now we're going to do a practice problem with this. So here the practice problem, decide whether each of these changes from X to change 1, 2, and 3. If it's possible, if it is possible, decide whether it's a physical or a chemical change. The first thing we need to point out and consider is the principle of conservation of mass, meaning that nothing can be created nor destroyed just out of nowhere. So here we know we're going from substance X into one of these. It's not saying that anything else is introduced to the system. So one thing we will check is this conservation of mass. Do we have all the same components here and then they're all the same components there, or did something just magically appear in the box? And if it did magically appear, then that would not be abiding by this conservation of mass principle. Then as we are differentiating between a physical and a chemical change, going back to what we know about both of those, the chemical change will involve altering the composition or identity of the substances involved, meaning that we're not just melting the chemical from a solid to a liquid, where in that case, if we're melting, that's an example of a physical change. But for chemical changes, if we are actually changing the identity of the substance, it might mean we're burning the substance. For example, when hydrogen gas or H2, this is one of our diatomics, right? If H2 gas burns in air which contains oxygen to form water, we are completely changing the identity of hydrogen gas and oxygen gas to form just an entirely new chemical or compound. So that's an example of a chemical change. We're actually changing the identity of the substances involved. There is more detail and examples of chemical versus physical change in your chapter 1 PowerPoint slides. Now, on the other hand, we could have physical changes. This does not alter the composition or identity of a substance as mentioned. For example, if we're taking solid ice water or melting it to liquid water, it's still the exact same substance. So it's still H2O, but it's not going to be in its liquid state anymore or its solid state. But this is still H2O as a solid, and liquid water is also still H2O. So this solid to liquid change, that's an example of a physical change. Another example of a physical change here is if we are dissolving sugar in water. Again, importantly, because as we've talked about, both sugar and water, even when dissolved into a solution, will both retain the properties of their physical identity. Again, water is not chemically altered, sugar is not chemically altered, they're just physically mixed together into a solution. So now let's start to solve this. And we said that one thing we would definitely check is the conservation of mass. So to start out in characterizing what sample X is, we have definitely a diatomic element, right? It could be one of the Brinkelhoffs. It has to be one of the Brinkelhoffs. There are 1, 2, 3, 4 times 3. There's 12 of these diatomics, and that gets broken down into 24 different atoms or elements. You'll see more on atoms and elements in chapter 2, but each of these is an atom of a certain element. So now for change 1, we are seeing the appearance of these black spheres that were not originally present in substance X. So this is disobeying this principle of conservation of mass, meaning that change 1 here would be impossible. So next, now for change 2, let's go ahead and check. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 molecules. And did we gain or lose anything along the way between this box and this box? Well, no, we still have 24 different atoms or elements present. They just appear in a different composition. So what does that mean then? We did obey the conservation of mass because nothing new was added or taken away. But what we are doing is that we are chemically altering the composition. So it's going from, let's say, maybe this is H2 or Cl2, and then this is 3 of those atoms together. This could be Cl3 or H3. Not that these exist in a very stable manner, but just for an example here. So this is a chemical change because this is chemically altering into a different kind of compound. Now, the next one here, this does also obey the principle of conservation of mass. We still have 4 times 3. We still have 12 of these different diatomic elements present. And the only thing we can see that looks different is the directionality of these diatomics. So first they're kind of pointing this way. And then in this format, they seem to be altering like this. So they're not chemically changing. The change is possible because it does obey that conservation of mass. And so the only option left here is this must be a physical change. Again, because these are not chemically altering, there's just a slight difference in the physicality of these diatomics in this box versus this box. The next highlighted topic we'll get into is converting between Celsius and Kelvin. We'll also throw some Fahrenheit in there just for practice. Here for this problem, we are going from Kelvin we're asked to convert it into degrees Celsius. Now for the conversion factor, we will need to know here is that the temperature in Celsius will equal the temperature that's in Kelvin minus 273.15. So here is our temperature in Kelvin. We'll go ahead and plug that in here. So 0.273 0.0003 Kelvin minus 273.15. That will equal our temperature in Celsius. So for that, we should get negative 273.1497 degrees Celsius. Now, in deciding on sig figs here, technically we're doing a subtraction. So for addition or subtraction, to know the number of sig figs we can have in our final answer, we look at the number of digits past the decimal place. Here we have 1, 2, 3, 4. This we're considering sort of a conversion factor or an exact number. So for conversion factors or exact numbers, we don't take those into account when deciding how many sig figs past the decimal place we should have for addition and subtraction problems. We also don't include the conversion factors for multiplication or division either. Now then we have 4 digits past the decimal place, so we can have 1, 2, 3, 4. So this is indeed our final answer. For this next problem, we're asked to go from degrees Fahrenheit into Kelvin. Now there is a way to go straight from Fahrenheit to Kelvin, and I'll write that out for you. You can also go to Celsius first and then go to Kelvin. So this set of conversion factors here goes from Fahrenheit into Kelvin. Let's go ahead and go into Celsius first just to do it. So this is our conversion factor between Fahrenheit and Celsius, and here we have Fahrenheit, and we're going to end up solving for Celsius. So let's go ahead and rearrange this equation. So to rearrange this, we're going to subtract 32 from both sides. Again, we want to isolate just the Celsius part. I'm also going to flip these around, so put 9/5 times degrees Celsius equals, and now we can do this part. This is degrees Fahrenheit minus 32. Then to further simplify this, we want degrees Celsius on its own. That means we need to multiply both sides by 5/9 in order to cancel out these fractions. That means that degrees Celsius will equal 5/9 times degrees Fahrenheit minus 32. Now we can go to Celsius as an intermediary. We can also show how we get this equation. So we have degrees Celsius equals this in terms of Fahrenheit, but ultimately we want Fahrenheit and Kelvin connected. So the other conversion factor we know is that Kelvin is equal to degrees Celsius plus 273.15. From this slide, we also know that the temperature in Celsius is going to equal the temperature in Kelvin minus 273.15. So it's just a rearrangement of this equation. So we rearrange that equation. What we could do next then is to plug in this meaning of degrees Celsius into this part of this equation. What we will get in the end is this one here. So I'm showing you this worked out in case you want to practice this. So degrees Celsius is equal to Kelvin minus 273.15. I went ahead and plugged that into this meaning here for degrees Celsius. Then if we want to isolate Kelvin, like it's showing up here, then we would add 273.15 to both sides. And then we end up with this equation here to go straight between Fahrenheit and Kelvin. Now we're ready to solve this problem. So Kelvin equals 5/9 times 98.6 degrees Fahrenheit minus 32 plus 273.15. We are going to practice the correct order of operations here. If you remember PEMDAS, meaning we will do whatever is in parentheses first. So we do this first, then any exponents, if there are, then multiplication/division, whichever one shows up first in order from left to right, and then your addition and subtraction. So we'll do whatever's in parentheses first. So we took care of this first, then the next step would be to multiply these two, so 5/9 times 66.6. That gives us 37, and now plus 273.15, and we should get, so here we should get 310.15 Kelvin. Going back to the number of sig figs again, we did subtraction here, and then all these other values are part of our conversion factors. So the only one we really want to keep in mind is this one, which has 1 digit past the decimal place. So let's go ahead and round this, and that will make this for 1 digit past the decimal place. We can either keep this as a 1 or this rounds up to a 2. And because this is 5 here, so 310.15, that means we round this up to 2 for our final answer, 310.2 Kelvin. If this number here were between 0 and 4, we would keep 1 as 1, but between 5 and 9, that means we round that digit up. So that is our final answer, and there's one more practice problem we'll do. Here we're instructed to go from Kelvin to Fahrenheit. And we could rearrange this equation in terms of Fahrenheit and then be able to plug in a value for Kelvin. I will go ahead and give you that conversion factor, but feel free to practice doing that rearrangement of that formula on your own. So here we have degrees Fahrenheit is equal to 9/5 times Kelvin minus 273.15, then plus 32. Let's plug in our values here. So this is 70. And we would do whatever's in parentheses first again. So 273.15, 70 minus that. So we'll have this now, and then we would do the multiplication next, and then deal with the addition and subtraction. So that gives us, then for the addition for our last step, that gives us, and now figuring out the sig figs for this one is a little bit different. Let's go ahead and say that the number was formatted like this. That means that we have no digits past the decimal place. Here as well, this would mean no digits past the decimal place. So theoretically, we should change this into this value having no digits past the decimal place, meaning we would stop right here. And because this is a 6, this means we will round that value up, meaning our final answer here would be negative 334 degrees Fahrenheit. So our final answer has no digits past the decimal place, and again, because this is a 6, it means we need to round that value up, so this is our final answer. The next topic here we talked about at the beginning, so calculating mass density. So we know density can be represented by the symbol rho or d, and density equals love, meaning that it equals a mass measurement or value over a volume. So here for this question, we have a volume and we have a mass. We're told to round our answer to 3 sig figs, and we want the density in units of grams per centimeter cubed. Notice that right now the volume is in terms of liters. One thing I want to point out with fraction representation of units like this and using negative exponents, know that this grams per centimeter cubed would also be written like this, so grams per centimeter cubed. And then if you remember these rules for exponents, because this is in the denominator, if we change this to have a negative exponent, then we can bump that up into the numerator, meaning that all of these are the same thing. This is still grams per centimeter cubed, or we would say this is grams times centimeters to the negative third. But this is all the same thing as grams per centimeter cubed. One conversion factor that will be extremely important as we go along in the semester is knowing that 1 centimeter cubed is equal to 1 milliliter. Now, why is that? How can we picture that? Well, if you think of milliliters as far as volume, let's say we have a beaker, then this is filled with a certain amount of milliliters. Now, a centimeter cubed, you can think of that as 1 centimeter by 1 centimeter by 1 centimeter. When 1 centimeter is cubed, that is the equivalent of exactly 1 milliliter. So I also added here that this is rho is equal to density is equal to mass over volume. So we already have a gram amount. So we have the mass there. The problem right now is that we need to take the volume in liters and eventually convert that into centimeters cubed. Based on what we just found out, if we convert this volume from liters into milliliters, then we know that 1 milliliter is actually 1 centimeter cubed. So then we would be done after we convert that into milliliters. So what we need to do in setting these up is you always want to write whatever value is given to us. And then to set up the conversion factor, we know that 1,000 milliliters is equal to 1 liter. So when we're deciding how to orient this conversion factor, it can either be oriented as 1,000 milliliters is equal to 1 liter, or 1 liter over 1,000 milliliters. These are the same thing, and depending on what unit we started with, we can reorient this as we need to. So here we want to cancel out liters, meaning we'd want to orient the conversion factor like this. So we could say 1,000 milliliters over 1 liter, meaning we could cancel out liters and just leave milliliters, which is exactly what we want to do. So if we solve for that, that is going to be 591 milliliters. How many sig figs should we have? This is a conversion factor. We don't need to pay attention to that 1,000. We're doing a multiplication or division problem, meaning that instead of looking at the number of sig figs past the decimal place or digits past the decimal place, we want to look at the number of sig figs. So for multiplication and division, we just look at the number of sig figs. And here in this original value, there are 3 sig figs, 1, 2, 3. This leading 0 is not a sig fig. So right now we could keep this as our answer. This also has 3 sig figs. Now I'll show you this conversion factor as well, just so you start to get used to it. I mentioned that 1,000 milliliters is equal to 1 liter can be written as either this fraction or this fraction. Same thing goes for this, even though we don't really need to explicitly show it, it's good practice to get used to. So if we write this equal sign, we can also represent those fractions as 1 centimeter cubed is equal to 1 milliliter, or 1 milliliter is equal to 1 centimeter cubed. So because we have this value in milliliters and we want to be able to cancel out milliliters and just have centimeters cubed, then we want to use this version of the conversion factor and say 1 centimeter cubed over 1 milliliter. Milliliters would then cancel out and we'd be left with just units of centimeters cubed. So because we're just multiplying by a factor of 1, this is still 591. But instead of using milliliters, which got canceled out, we're going to say this is 591, centimeters cubed. Now for the last step, we need to take the mass, or 370 grams, divided by 591 centimeters cubed. We can see that when we are dividing and deciding on the number of sig figs in our final answer, there are 3 sig figs here. This decimal point is here, so 1, 2, 3. That's also 3 sig figs. So our final answer, or let's first do our unrounded answer. So that is 0.62605 grams per centimeter cubed. When we round that to only 3 sig figs, 1, 2, 3, that 0 means we will just keep that 6 as a 6. So we have 0.626. This doesn't round up to 7 grams per centimeter cubed. And that is our final answer. We were also told in the problem to round to 3 sig figs, but be sure you're comfortable figuring out the proper number of sig figs just based on the original starting values alone. You won't always be told how many sig figs to round to, so again, be sure you're comfortable figuring out how many sig figs should be in your final answer. There's different rules for multiplication and division, and then addition, subtraction. Addition, subtraction, remember, was looking at the number of digits past the decimal place, whereas for multiplication and division, we're looking at just the total number of sig figs. Now, speaking of sig figs, we're going to go into this topic a little bit more on counting sig figs. One big idea that goes into and is related to counting sig figs is being able to write these numbers in scientific notation. The main thing I want to point out from this slide that is available in your chapter 1 slides is that if we have a really large number that's greater than 0, right, that means greater than 0, we'll have a positive exponent here. Also, to get that positive exponent, we would take the placement of the decimal point being here or here, and then we move it over 1, 2. We want just one number on the left-hand side of the decimal point, and then we would say times 10. And then because we move that decimal point over 2 times, then we have a 2 here. Over here with values that are less than 0, again, we would take the placement of the decimal point, but instead of moving it to the left to get to this spot, or here, and then to get to this spot, remember we want just one number to the left of that decimal point after we make the value into scientific notation. So like that's a correct form of scientific notation, and this is a correct form. If you saw something like 56.87 times 10 to the 1, that is not the correct form of scientific notation. Again, only have one value past the decimal point. And again, for these values that are less than 0, we would move the decimal point over to the right to get to this point. And then however many times we move it, 1, 2, 3, 4, 5, 6. Then we put 6 here. Because that value is less than 0 originally, that is a negative exponent, so -6. One thing I want to clear up as I was talking about this, realize that this number is greater than 0. This full number is also greater than 0. So what I should have said for these n is greater than 0 and less than 0, this refers to the exponent here. Okay, so this is a negative exponent here, so that means that n is less than 0. And then for this exponent here, n is greater than 0. So what should have been said for these is that this number here is greater than 1, right? In this case, it's a lot greater than 1, the number itself. This number here is less than 1, so then that leads to it having a negative exponent. This number here is also less than 1. Another number that is less than 1 is even 0.9. That's just slightly less than 1. It would still end up having a negative exponent. Let's say the value is 0.90. To make this into scientific notation, we'd move that decimal point over 1 to the right. So this would be 9.0 times 10 to the -1. We moved it one space to the right, meaning we're going to end up getting an exponent that is a negative value. It's less than 0. So hopefully that clarifies. Let me know if you have any questions about this, as always. Now, just as we did here, you should also be comfortable going the other way. So if you had a number in scientific notation and it says times 10 to the -6, that means to get out of this and into just a regular number, you'd actually want to move the decimal point over back to the left. So you're sort of doing the opposite of what we show here. And also for these positive values, you again want to know how to do that as well. If you saw this times 10 to the 2, it means we would take that and go 2 times to the right to get back to the original number that we were dealing with. Again, so sort of the opposite process from taking a number and then putting it into scientific notation. You should also be able to take a number in scientific notation and get it out of scientific notation. So let's do a little practice here. Another clarifying point here that I will change in the slides that I post for you for these highlighted topics. This is a number that's greater than 1. This is a number that is less than 1. The exponent itself here ends up being a positive exponent. And then the exponent here ends up being a negative exponent. So here's our decimal point. We want to go 1, 2, 3 times to the left. This becomes 5.960 times 10 to the 1, 2, 3. Importantly, I'm keeping this 0 in here because it is a sig fig. And it is a sig fig because we have that decimal point there, meaning that we do count this 0 as part of a significant digit that matters for that value. Now we'd recognize this example being a number less than 0, so we would go over 1, 2. We only need to go 2 times to the right, and then that makes this 5.960 times 10 to the negative 2. Right, because we went over to the right 2 times. Here, we went over to the left 1, 2, 3 times. So make sure you're really comfortable doing this step. Just to check, these are the correct final answers. Next, this set of rules is available in your Chapter 1 PowerPoint slides. Just to go over these, any digit that is not 0 is always going to be significant. So that is one of the rules here. Zeros between non-zero digits, those are also always significant. So the 0 here, that still counts as a significant digit. Now, number 3 can get a little bit confusing, but zeros to the left of the first non-zero digit are not significant. If this were 0.00008, these are also still not significant values, for example. Then being able to differentiate here is a number greater than 0 or less than 0. For number 4, if it's greater than 0, all zeros to the right of the decimal point are significant. Importantly, all zeros to the right of the decimal point, meaning that decimal point has to be present. So 2.0, that decimal point is present. 2.0 is a value that's greater than 1. And because this number is greater than 1, then all these zeros are indeed significant, meaning this has 2 significant digits. Now going on to number 5, if a number is less than 1, then only the zeros that are at the end and in the middle of the number are significant. So if they're in the middle, this comes back to rule number 2. So that's one we've seen before. So that at the end and in the middle. So at the end, that means that this is a significant digit. Okay, so it's getting more and more precise as you are able to add on these zeros here. So all of these would be considered significant. Let's try this now. So let's determine the number of sig figs in all of these examples. So this first one here, we have a number that is less than 1. So we would follow step 5. So any leading zeros are not significant, but any zeros that come after the first non-zero values or they're in between non-zero values, those will be significant. That means for us here, these leading zeros are not significant, but here these two are, so we have 2 sig figs. The next one here, this also relates to this rule number 5. So we would say that these again are not significant. These are. This one, based on rule number 5, it comes at the end of numbers that are significant. So the 4 and the 3 are significant. This 0 does come at the end, meaning this is 3 sig figs. Now this one here I fixed, so this is a number greater than 1. So here we have 1, 2, 3, 4. We have 4 total sig figs. This number here also counts as a sig fig. Going back to rule number 4, the number is greater than 1. All zeros to the right of the decimal point are significant. So here we do see the decimal points present. All numbers here to the right of the decimal point will be significant. This one is another example of a value that's less than 1. So 1, 2, 3, 4. This also has 4 sig figs. This 0 that comes at the end, that is a significant digit. For a little bit more of an explanation here written out, I did write out this little bit here. So this one does indeed have 2 sig figs. This one has 3 sig figs. Again, I wrote out the number of sig figs here as well. This has 4 and this has 4. The next topic here is counting sig figs when we are doing addition or subtraction. We have alluded to this throughout this recording, and we'll do some example problems now. So here we're going to practice adding and subtracting, and then determining the number of sig figs. So when we are adding or subtracting, again, we want to just pay attention to the number of digits past the decimal place to tell us how many sig figs we should have in our final answer. So when we do the math here, we will end up getting 30.470 Technically, the unit is in milliliters. Now, the important part here is to say that this has 1 digit past the decimal place, 1 sig fig past the decimal place. This has 3. So we're going to go with the fewer in our final answer. So the final answer can only be as precise as the numbers that were involved in the calculation, meaning that we need to go for the fewer number. We can't just magically make this have 3 sig figs. We need to accommodate for the value with the lower number of sig figs in our final answer. That means that we will round this to 1 digit past the decimal place, and that means that this 7 bumps this up to a 5. Our final answer then here is 30.5. Don't forget the unit if you have the option to put that in. So that is 30.5 milliliters. The next one here, we have 2 sig figs past the decimal place. Here we only have 1. So in our final answer, we need only 1 digit past the decimal place. Doing the math here, this is going to be 8.81 milliliters. Then to round this to only 1 digit past the decimal place, this 1 keeps the 8 as is, meaning our final answer is 8.8 milliliters. Now this next one might look trickier because we are going to do an addition problem, but with 2 values that are in scientific notation. When 2 values are in scientific notation, we can follow this set of rules to help us solve that. So to solve these kinds of problems, we are going to get each quantity to have the same exponent n, then we'll add these values here, and then we'll keep n the same. So let's try it together. So right now, this exponent is a 4, this one is a 3. To get these to have the same number of exponents, the easiest way is to make this 3.9 times 10 to the third, make the value with the smaller exponent into a value that has the greater exponent. So we need to match these two. It's easier to make 10 to the third into 10 to the fourth. It's slightly easier rather than taking 10 to the fourth and putting that into 10 to the third. The general rule here, and this is in your chapter 1 notes, when we move the decimal point 1 point to the left, move it to the left, then we add 1 to the exponent. So when we rewrite this, it becomes 0.39 times 10 to the fourth. Now we're ready to take this and we're going to add 4.31 times 10 to the fourth. These have the same exponent now, meaning we can just add these together because we were told to add. Then we'll keep this part of the final answer the same. So that becomes 4.70 times 10 to the fourth. To check the number of sig figs here, we have an addition problem. Yes, this is multiplied by 10 to the fourth, but really we just have an addition problem in the end. So we're looking at the number of decimal places, the number of digits past the decimal place. Here then, actually, we're going to go based on this one. This has 2 digits past the decimal place. This has 2. So our final answer can have 2 as well. So that will be our final answer. Here are these rounding rules written out just to have for you as well. We've talked through them quite a bit, but here they are written out as well. The next topic here is counting sig figs, but for multiplication and division. So we've talked about this as well, and we'll do some practice problems. So generally for multiplication and division, we are going to just keep the total number of sig figs that was in any of the original values. That total number of sig figs, we'll look at the fewest number of total sig figs in either of the original numbers, and then that will become the number of sig figs in our final answer. So for this first one, I'm going to rewrite this just a little bit for ourselves. So we know that grams per milliliter can really be written as this fraction times 80.0 milliliters. That means as far as units at least, it does make sense that milliliters and milliliters cancel out, and then we just have grams in the end. Now when we do the multiplication for that, we will get 6248 grams. But what we need to do is make this into just 3 sig figs total. So we'll stop there. And we will allow the 8 to bump this 4 up to a 5, meaning 6250 is actually the correct number of sig figs here for our final answer. If we wanted to, we could put this into scientific notation. We could say that this is going to move over 1, 2, 3 times. So 6.25 times 10 to the positive 3. Our final answer, again, can only have 3 sig figs, so we don't include that 0 as one of our sig figs. So this would be our final answer, again, with the unit of grams. Now, another concept that will tie into addition and subtraction like we did, so we can also do multiplication and division, but when we have numbers that are written in scientific notation. To cover those rules here, we are going to multiply or divide n and n2, and then depending on whether it's multiplication or division, if it's multiplication, we are going to add the exponents. If it's division, we are going to subtract the exponents. So let's go back and do those example problems. So let's try this one now. We know we're going to multiply these values and then we'll deal with the exponents. When we multiply those values, that's definitely 28. And now for multiplication, we're going to add these exponents. So we still write out times 10. And then once we add -5 plus 3, that gives us -2. Now, this number, as we know, does not look like it's in proper scientific notation because there should just be one value past the decimal place. So let's go ahead and finish this and write this in scientific notation, correct scientific notation. That means our decimal point is here. We're going to move it 1 to the left, and we will add 1 to that exponent. So that gives us our final answer of 2.8 times 10 to the -1. Now we don't have units here. I should check the number of sig figs before squaring that or circling that. Here we have two sig figs in this number. We also have 2 sig figs in that number. That means that we can have 2 sig figs total in our final answer for this multiplication problem. Now this example here, we will divide these based on the rules we looked at. That gives us a number of 2. We'll deal with sig figs at the end. Then we're told to actually subtract these exponents. I'll write in this now because we will do that. We divided these times 10 to the something. To figure out that exponent, we know we need to take that first exponent minus the second exponent to give us -2. That means that this exponent is -2. To write this with the correct number of sig figs, this has 2 sig figs, this has 2 sig figs. That means we should say 2.0 times 10 to the -2 as our final answer. The last topic here is doing some adding or subtracting and multiplying or dividing of measurements. So one thing we did mention and talk about just briefly is to be sure to be following PEMDAS, anything in parentheses first, then exponents, then multiplication or division, depending on the order. As the multiplication or division appears, you want to follow the order from left to right. And you can see this example here if you would like more practice on that. Then lastly, we would do the addition or subtraction, also again, in order from left to right. For example, if on the left-hand side, addition comes first before subtraction, then we do the addition first. If it were the other way around, we would do subtraction first, excuse me, and then addition. So definitely look at this practice problem if you would like a refresher on using PEMDAS. Now, the practice problem that can involve some multiplication, division, addition, subtraction, a combination would be an example like this. We're told that an empty graduated cylinder weighs 3.000 grams. When I get the right number of sig figs, it would have these markings here, and then it might be filled with, here it's filled with a solid. So once we add in solid, then we reweigh that, and then everything together we're told weighs 89.8 grams. Now we know the mass of the solid. We could figure that out if we subtracted these. Let's keep reading through. Water was added to the graduated cylinder and dissolved the sodium thiosulfate completely. the total volume of the solution from the markings on the graduated cylinder. If we are looking at, we're looking at eye level here, which we'll practice doing in lab, looking at the meniscus, then we're told this is a volume of 31.6 milliliters. Now for our problem, we're going to calculate density in grams per milliliter, which we know can also be written like grams per milliliter or grams times milliliter to the -1 exponent if we wanted to. Now the first thing we can do is to figure out the mass of the solid. So we know that 89.8 grams minus 3.00 grams, just the mass of the graduated cylinder, minus the mass of the graduated cylinder plus the solid. That's going to give us just the mass of the solid. So here we're doing a subtraction problem, and I left out one sig fig that would be important potentially. And when we do the subtraction problem, we will get 86.800. Now, before moving on to the next step, because this is subtraction, we can have either 1 digit past the decimal point or 3, and we are going to go down to 1, right? So this is going to be 86.8, just 1 digit past the decimal place. So that's the mass of the solid that we have so far. Now to finish solving for density that we know is mass over volume, then we have our mass, we have our volume, we just need to put those together, know that we're doing a division problem, and then have the correct number of sig figs for a problem that has division in it. When we take 86.8 grams divided by 31.6 milliliters, we should get a number that goes on some, so 2.7468 grams per milliliter. Because we're doing division, we can look at the total number of sig figs in both of these original values. So 1, 2, 3, 1, 2, 3. That means that our final answer for this division problem should just have 1, 2, 3 sig figs. This 6 will bump that 4 up to a 5. Then for the units, we can format them in whatever way you'd like. It can also be represented like this, the grams per milliliters to the -1. We know that that really is grams per milliliter, also written like grams per milliliter. We're at the end of this highlighted topics video, showing some practice problems. As always, let me know if you have any questions, and I will talk to you all soon.